So a really large part of calculus is the study of motion, and physics and calculus together are kind of a study of motion. And we're going to focus a lot in our class at this level on motion on a line. And so there's all these different examples and problems that we're going to study, but a really standard typical problem is like the motion of a car driving down a road. And we can analyze that car traveling on a road based on time. We can set a timer and we can say, from time A to time B, how fast does the car go? How far does the car go? What's its average rate of change? What's its instantaneous rate of change? We can ask a lot of different questions and really analyze it. So we're going to get into that a little bit more, and we're going to take some notes on some different topics. The first way we can analyze the car driving down the road is we could talk about its displacement. So displacement. And what displacement is it's this net change in the position of the car. So when somebody asks you about the displacement of a moving object, it's the net change in its position. And a lot of times we denote it with a function like x of t. We make up some sort of an equation to represent the change in position. But when I say change in position, I often think of the delta x. Remember the delta symbol, the little triangle symbol here means change. So delta x is going to be the change in position. And when we're studying the position, we study it on time intervals. So on this graph over here, we have an xy axis where the x-axis represents time and the y-axis represents the position of the car. And we could study it from a time interval, we'll say from A to B, where A could be like 3 seconds and B could be like 20 seconds, or 3 minutes and 20 minutes, or 3 hours and 20 hours. It's some sort of time notation. And what we're going to end up doing is we're going to end up finding the change in position on that time interval. So we're going to take the position at x of B and we're going to subtract x of A. And that is the change in position. And so on a graph, it's going to look something kind of like this. Let's make up a graph of this car. Let's say the car started at 0 seconds in a 0 position and then maybe did something like this. And this graph, I'm totally making it up, is going to be our x of t graph, our position graph. And what we could analyze and really study on the graph is we could look at what's going on at time A, where's the car, and what's going on at time B. And over on the y-axis over here, at those points, at A and B, those are our position points. So maybe the car is, 7 miles away at time A and 10 miles away at time B. Well, what's the net change in the position of the car? Well, it traveled from 7 miles to 10 miles. That's a change in position of 3 miles. So you'd say its net change is 3 miles. It went a 3-mile distance. Well, that net change is also called the displacement. So it was displaced 3 miles. And so when we go to write our answers for these problems, the units of measurement are always position measurements. So your answers are going to be in things like feet or meters or miles or inches, anything that measures a position. So feet, meters, miles, inches, yards, I'm going to write etc. And the answer can be either positive or negative depending on which direction it moved, if it went backwards or forwards. So you can get a positive or a negative answer for these problems. So this is kind of what displacement is all about. And when we graph it as a time and position graph. And the units can be in feet, meters, miles, etc. And they can be positive or negative. Now, to change this a little bit, we could start asking questions about the car and say, well, how fast is the car going? And that gets us into what we call velocity. And so velocity is kind of our next step up from displacement. And what it is it's the change in position. Notice I wrote it up here, the change in position, just like displacement. It's displacement, but it's with regard to time. It's how fast is the change in position happening. So it's the change in position divided by the change in time. And so when we go to graph it, we graph it on a time and velocity XY axis, a time and velocity graph. And so velocity, let's write a little note over here. When we measure it, the units are how fast something's happening. It has to do with the speed of the car. So it's in things like miles per hour, or, it could be a different moving object, so it could be something like feet per minute, or we could say yards per hour, or inches per second. I could make up a bunch of these, inches per second, etc. It's some sort of rate, some sort of speed. So miles per hour, feet per minute, yards per hour, inches per second, etc. And so on the graph, what's going to happen is now when we measure that time, let's say we had that car from time A to time B. Well, now the graph could look, it could look a lot different than what I had originally. Maybe it's going to be something more like this. Let's say it starts out at 0, maybe goes like this. Now we're going to denote this graph. Instead of calling it x of t, we're going to call it v of t for velocity. So this net change in position divided by the change in time equals v of t, velocity. And the points on the graph where A are, let's say it's right around here, and where B are, over here on the y-axis, represent how fast the car is going. Maybe at A, the car was traveling 25 miles per hour. Maybe at B, the car is traveling 30 miles per hour. It's that rate of change. How fast is the car going? So the units for velocity can be measured, and they can be positive or negative, which gets us into an interesting conversation of how can you have a negative speed? How can a car be going negative 30 miles per hour? What does that mean? So velocity gets its own name. It's a little bit different than speed, and we're going to talk about it here in a second. Let's go to a different slide here. Speed is the absolute value of velocity. So when we talk about speed, it's really the absolute value of velocity. And I'm going to write it as a definition for our notes, absolute value of velocity. Speed on a speedometer on a car is always a positive number. You never drive in your car and look at your speedometer and say you're going negative 10 miles per hour. That never happens. You're always going from 0 to 60, 0 to 70, whatever, but you're never going a negative number. Negative numbers would refer to you going backwards. So what I'm going to do is make a little chart here. We need to compare speed versus velocity, because although they're kind of the same thing, they're also kind of not. So we have to be real careful about this. It's quite a difference between speed and velocity as we get into our physics and calculus. So speed, we say, is a scalar quantity. A scalar quantity, and we'll talk about that. Versus velocity, we say, is a vector quantity. A vector quantity. We'll write that down. Now, a scalar quantity and a vector quantity are referring to different measurements. A scalar quantity is how fast the object moves. So when I'm talking about a scalar quantity, I'm talking about a number that represents how fast the object moves. So I'm going to write that down. How fast the object moves. Versus velocity. Velocity is the rate at which the object is changing its position. So it's still kind of a how fast is it happening, but we often just refer to it as a rate at which the object changes its position. So a rate at which the object changes position. A rate at which the object changes position. And although these are very similar, there are some differences. Speed is always going to be positive. Velocity can be either or. So we denote velocity with the v of t equation. We denote speed also with the v of t equation, the velocity equation, but we say it's the absolute value of it. It's the positive number. And that's going to come into play as pretty important later on. I think let's do this. I'm going to erase this page here for a second, make some space here. just to kind of clean some of this up. If velocity, I think this is important to write down, if velocity ends up being a positive number greater than 0, so we'll write that down over here. If velocity ends up being positive, then you know that your object is always moving in a positive direction. So velocity being positive means that the object that's moving is either going to the right, so I'm going to write object moves to the right, or maybe we're talking about an object that's going up or down, so this positive velocity would mean it was moving up. So a positive number for velocity means the object it moves to the right or it moves up. A negative velocity, if v of t is less than 0 and it's a negative number, refers to the object moving left or down. So the object moves to the left or it moves down. And then there's one more scenario that could possibly happen. We could have velocity equal to 0. And if that's the case, the object's not moving left, it's not moving right, it's not going up, it's not going down, it's stationary for that moment in time. So this is when you know the object's not moving at all. It's a stationary object. So no movement. And these are the 3 different velocity situations that we can have. So when you get a positive velocity number, it tells you a lot more than just the speed. It tells you that the object itself is moving to the right or moving up. And that's pretty helpful information. So going back to velocity a little bit here, besides knowing if it's positive or negative, there are 2 types of velocity calculations that we're going to have to kind of talk about. The first type of velocity calculation, number 1 here, is the average velocity. So average velocity. And average velocity, I always make the joke in class that anybody can do an average velocity, an average person can do it. But what it is it's kind of like an average rate of change, which we've been learning about in class. I think average velocity and I think average rate. So like on a graph, it's a secant line. And what you're basically doing is finding the slope of a secant line. And we denote it like this a lot of times. Average velocity is the change in x, the change in the position of the car or the moving object, divided by the change in time, on average. So if I said, what's the average that this thing moves from A to B, then you'd say, well, I'll take x of B minus x of A, that's that displacement equation, and I'll divide it by the change in B minus A, where A and B are time. A could be 3 seconds and B could be 20 seconds or whatever. And so you're using those numbers to find the average, this average velocity. The other type of velocity that we're going to use much more often is called the instantaneous velocity. Instantaneous velocity. And this is where you want to know what's the velocity of the moving object at that very second moment in time. Like right then and there, how fast is this object moving? So I think instantaneous rate of change, and I think of a tangent line, which we've been learning about in class. And so when I refer to instantaneous velocity, it means that very second in time. So we gotta get really, really close to turning this into a tangent line. And so we say instead of finding this average rate of change formula up here, instead what we're gonna do is we're gonna find velocity through the derivative process. We're gonna derive this whole equation. So we're gonna take x of t from earlier, the position equation, and we're gonna derive it. Other people sometimes denote it like this. Other people, this is just another way of doing it, but it's the limit as our change in time approaches 0 for this delta x over delta t formula. If you're going to do the old limit process, you'd be setting it up kind of like this. And this old limit process way is really the way of finding the derivative. So instantaneous velocity requires a derivative. Average velocity, anybody can do, you don't need any derivatives for. So these are your 2 types, instantaneous and average velocity. So with that in mind, let's talk about acceleration. Acceleration is the rate of change in velocity. How fast is the car speeding up? How slow is the car speeding up? If you're in your car driving and you're hitting the accelerator as hard as you can, that's an acceleration and we got to measure it somehow. So the same thing kind of occurs there are two types of these. Type 1 is you can have an average acceleration, and I'm going to write average acceleration down here. And type 2 is you could have an instantaneous acceleration. And you can measure both of those. And so we're going to just kind of briefly talk about this and then have to work on it more in class. But average acceleration and instantaneous acceleration, the way they work is a measurement of velocity. How fast is the velocity changing? So for an average acceleration, we would say it's the change in velocity with respect to the change in time. For an instantaneous acceleration, we would say, well, why don't we call acceleration a of t, an acceleration formula, and we'll find it by deriving the velocity equation. Or you could say it's the limit as the change in time approaches 0 for this average acceleration delta v over delta t. But again, this is the old longhand way of saying let's find the derivative. So we have average and we have instantaneous. Now a little bit of a note down here. The units for acceleration are kind of odd. Remember how the units for velocity are like miles per hour, feet per second? Well, for acceleration it's like miles per hour squared or feet per second squared, meters per minute squared. The unit on bottom gets squared. So there, you can make up a lot of these, inches per second squared, etc. And just like velocity, you can get positive acceleration and you can get negative acceleration. So there is a positive or a negative acceleration that are allowed. So a few different types. So let's try a problem. We're doing all these notes. Let's do something here. So here's an example of a problem. Let's just give a try of one of these. So our example is we have the position of some moving object measured in meters and seconds given by this equation x of t equals t to the third minus 4t squared plus 3. This is the equation of the position of the moving object. Now I don't know what this object is. Is it a car on a road? Is it somebody walking? Is it a bug crawling down the street? I have no idea, but something's moving and we're measuring it. So I got some questions. First question, question A. Find the object's displacement on the interval 0 to 2. Find the object's displacement on the interval 0 to 2. So what I'm going to do is I'm going to go back and look at the problem here and notice that everything is moving in meters per second and that this equation tells me the position of the particle. And what I'm going to basically do is pull that out as the most important piece of this question. Find the object's displacement on the interval 0 to 2. Well, 0 to 2 seconds in this case. And so I know that displacement is really denoted as the change in x, delta x. And I want to find the change on an interval from 0 to 2. So what I really want to do is I want to find x of 2 minus x of 0. That means what's the position of the object at 2 seconds and 0 seconds, and we'll subtract it. So what I'm going to do is I'm going to plug 2 into my position equation. X of 2 means I'm going to have to do this. Let's make a big parenthesis here. I'm going to have 2 to the third power minus 4 times 2 squared plus 3. We'll plug all that in. Minus, I'm going to plug in 0. 0 to the third power minus 4 times 0 squared plus 3. And then all we got to do is clean up all this work for a little bit here. So I'm going to go down to my next line, start cleaning some stuff up. This one's not too bad to clean up because the zeros are going to cancel. And we have 2 times 2 times 2, we have 8 minus 4 times 4 is 16 plus 3 minus 3. And we can clean this up and we're going to end up getting negative 8 is our answer. So we got our change in position for delta x is negative 8, and you want to add on some units to this. Negative 8 what? Well, negative 8 meters. And this means our moving object must have moved 8 meters backwards on this interval 0 to 2 seconds. So it moved 8 meters. That's why there's a negative sign. It moved 8 meters backwards on 0 to 2 seconds. Okay, so question B. What is the average velocity of the object on 0 to 2? What's the average velocity of this object? Now, I see average, so I realize I don't need a derivative. Average velocity means average person can do it. From 0 to 2, I can figure this out. So I'm going to use my average velocity equation here for a second. And I know that to find average velocity, it is delta x divided by delta t. The change in x divided by the change in time. And I want to do it from 0 to 2. So I'm going to take x of 2 minus x of 0, and I'm going to divide it by 2 minus 0. Now we just did most of this math. X of 2 minus x of 0, this is displacement. We just did this on the last slide and got negative 8 meters. So I already know that this little portion right here equals negative 8 meters. So I'm going to write equals negative 8 over 2 minus 1, which is, well, 1. Why don't we just say 1? And negative 8 divided by 1. Oh, I made a mistake here. Sorry, let's backtrack. I meant to do 2 minus 0. 2 minus 0, that makes more sense. So it's negative 8 over 2, and negative 8 divided by 2 is negative 4. Which means my average velocity, I'll just write that over here, average velocity is going to equal negative 4, and negative 4, since it's a velocity, it's going to be meters per second. That's how fast, on average, this object was moving. Now, negative 4 makes a lot of sense to me because that means that the velocity equation is negative. Therefore, v of t is less than 0. So my object must be moving backwards, back to the left or down. So it's a left-moving object at a rate of negative 4 meters per second. Okay, so what about this? Question C. Find the object's velocity at time equals 2 seconds. Find the object's velocity at time equals 2 seconds. Now this is a specific time. So now we're talking about an instant in time. I didn't say on the interval 0 to 2. I said how fast, what's the object's velocity at time equals 2. So now what I'm trying to find is what is the velocity of this moving object at, let's say, 2. What's the velocity at 2? That's my question. So I'm not going to be able to figure this out right away, not until I do a little bit of work first. And the work is, I need to know, before I find v of 2, what's v of t even equal to? Now that's going to require a derivative. Instantaneous rate of change is a derivative. So I'm going to take this equation up here, this position equation, and I'm going to derive it using the power rule. T to the third is going to be 3t to the second minus 4t squared is going to be 8t. Plus the derivative of 3 is 0. So plus 0, let's erase that. We don't need that on there. So I have 3t squared minus 8t. There is my equation. Alright, well I want to know the velocity at 2 seconds. So now I'm going to find v of 2 by plugging 2 into my derivative. 3 times 2 squared minus 8 times 2. And a little bit of math, and I'm going to have an answer here. So I'm going to have 3 times 4 minus 16, which is 12 minus 16, which is negative 4. It just happens to be the same answer as earlier. So velocity at 2, v of 2, let's label all of this so it looks good. The velocity at 2, v of 2, is equal to negative 4. And since it's velocity, I need units on here. This must be how fast the object's moving, so I'm going to write in meters per second. This object, right at 2 seconds, is moving an exact rate of negative 4 meters per second. So obviously the object is moving to the left because v of 2 is a negative number less than 0. So I know that it's moving to the left, and I know it's moving exactly negative 4 meters per second. Alright, so one more question here. Question D. Let's find the object's acceleration when time equals 4 seconds. Let's find the object's acceleration. Now, acceleration, you could have an average or an instantaneous. And in this case, it says when time equals 4, so this is another instant in time. So I'm going to write it's an instant in time. And that means I want to find out what is acceleration at 4. So acceleration is often called a of t, so I want a of 4. what is acceleration equal to at 4? And I'm not going to be able to figure this out until I have an equation for acceleration. Now right now I'm back to this position equation again. So I need to derive it for velocity, which we did earlier. I'm going to power rule this thing. It was 3t squared minus 4 times 2 is 8t. But I want acceleration. I want one more derivative down, so I'm going to derive it again to get a of t. One more derivative. 3t squared minus 8t is going to be power ruled. This whole thing is going to turn into 6t minus 8. That's my acceleration equation. So now I have position, velocity, and acceleration. And I want acceleration at time equals 4. So I'm going to find in the next step here, maybe we'll do it over here, a of 4, by plugging 4 into 6t. So it's going to be 6 times 4 minus 8. And 6 times 4 is 24. So we're going to do 24 minus 8 is 16. And we're going to get acceleration at 4 is equal to 16. And 16 what? This is how fast the velocity is changing. It's changing at a rate of 16 meters every second squared. So I can write seconds squared. And that is my answer. So we are going to work on this in class a lot. This is a pretty big, long video. I apologize for that. But there's a lot to learn about these 3 levels. There's displacement, velocity, and acceleration. And they can get pretty complicated. So we'll continue to work on it. I hope this helped.